In this video, we continue our discussion of the charge carrier concentrations. In the previous video, you were introduced to density of states function, the Fermi-Dirac distribution, its Boltzmann approximation, and the Fermi level. We will now use these parameters to determine the charge carrier concentrations in thermal equilibrium. Let's make a little recap. First, we discussed the band diagram with its well-defined bands for the valence and electron energies, conduction electron energies, and band gap, where there are no energy states that an electron can occupy. Then we defined the density of states function. This function is material dependent. The density of states function, therefore, tells us the number of states available for an electron to occupy at a certain energy level for a given material. As you can see in this figure, in high purity intrinsic semiconductor materials, there are no energy states available in the band gap for an electron to occupy. Further, we looked at the occupation of the energy states. To this end, we introduced the Fermi-Dirac distribution function. This distribution gives the probability that a certain energy state with respect to the Fermi energy level is occupied at a certain temperature. The Fermi-Dirac distribution is a general rule applicable to electrons in all kinds of systems. The last step is to determine the charge carrier density of electrons in the conduction band, Ne, and of holes in the valence band, Pe. This is what the profile of the occupied states looks like. On the top, we can see the occupation of the conduction band states, and on the bottom, we see the occupation of the valence band states. So, how did we get to these profiles? Here, we see our profiles of occupied conduction and the valence energy states. The actual number of electrons occupying a certain energy level, N, is equal to the product of the number of available states, G, and the probability that a certain state is occupied, F. As we discussed, the probability of an electron occupying an energy level above the Fermi level increases with increasing temperature. However, as there are no available states in the band gap, no electrons will occupy an energy level in the band gap. If the temperature increases enough, which is already the case at room temperature, the probability of an electron occupying an energy state in the conduction band will become greater than zero. The density of states, or DOS, for electrons at energy levels in the conduction band is greater than zero as well. Consequently, at room temperature, some electrons occupy energy levels in the conduction band. If we want to know the total amount of mobile electrons, we have to integrate the carrier concentration N from the conduction band edge up to through the band. A similar equation is used for the number of holes in the valence band. However, remember that holes are simply the missing electrons at given states in the valence band. Therefore, we have to multiply the density of allowed states by 1 minus the occupation function to find out which states are actually unoccupied. Again, we can integrate this product to obtain the total number of holes in the valence band. If we use the Boltzmann approximation, we can calculate these concentrations. For electrons in the conduction band, we get this expression, and for holes in the valence band, we get this other expression. The full derivation of these equations can be found in the textbook. There are, however, two new parameters in the equations for carrier concentrations, Nc and Nv. We call these parameters effective densities of conduction and valence band states, respectively. At a given temperature, they are different from each other since the effective mass of electrons is different from the effective mass of holes. We note in these two expressions the conduction DOS mass and the valence DOS mass. For the case of silicon, despite electrons having a lower effective transport mass than holes, as previously mentioned, the higher multiplicity of the conduction band energy minima outweighs the lower mass of individual electrons, resulting in the conduction DOS mass being larger than the valence DOS mass. And this ultimately leads to a larger Nc compared to Nv. Now we get to an important property of semiconductors, the intrinsic carrier concentration, or Ni. Ni squared is equal to the product of N, the concentration of electrons occupying states in the conduction band, and P, the concentration of holes occupying states in the valence band. This product can be calculated as follows. In the simplified expression, we can see that Ni is just dependent on the band gap, the temperature, and the effective densities of states. In a full intrinsic semiconductor, since N and P are equal, they are both equal to Ni. For crystalline silicon at 300 Kelvin, Ni is equal to 10 to the power of 10 per cubic centimeter. We will use this value in many equations to come, so make sure to note it down. This graph shows the temperature dependence of the charge carrier concentration in intrinsic silicon. The value of Ni monotonically increases as the temperature increases. This is because with the increase in temperature, more thermal energy is available. Thus, more electrons are excited from the valence band into the conduction band. This lecture, we have learned how to determine the concentration of charge carriers within a semiconductor. However, this method is only valid for intrinsic semiconductors in thermal equilibrium. In the following videos, we will first see how the carrier concentration can be manipulated by doping the material. Afterwards, we will move our analysis to a non-equilibrium situation.